Hello and welcome back to the course Introduction to Green Process Engineering. In this video, we are going to focus on the transition pathway of the chemical industry. First, we will have a look on some key facts of the chemical industry, then the most relevant technologies fostering the transition of the chemical industry are summarized, accompanied by relevant industry examples. The European Union is the second largest chemical producer worldwide, with 1.2 million direct jobs supporting an additional 3.6 million jobs indirectly. Hence, the chemical industry plays a strategic role in Europe. Most of the goods that are manufactured in Europe rely on chemicals. They are, for example, used as solvent, catalyst, educts for chemical synthesis or lubricants. Chemicals are highly relevant for Europe's major value chains, including pharmaceutical, electronics, batteries, and many more. The chemical industry is responsible for 4% of the total CO2 emissions of the European Union, making it the third largest CO2 emitter in Europe. The transition path of the European Union is structured around 8 interconnected building blocks that you can see in more detail on the website of the European Commission. We will have a closer look at the relevant technologies. But what are the most relevant technologies within the ongoing transition of the chemical industry? As you can see here, 6 main routes are defined, including electrification, hydrogen with a low carbon footprint, biomass, the utilization of waste, carbon capture and utilization, in short CCU, and carbon capture and storage, in short CCS, and process efficiency. What do the most relevant technologies now involve? Let us have a closer look at the single technologies on the next slides. Electrification involves the direct and indirect use of electricity in chemical processes. Both are distinct measures to reduce the carbon footprints in the chemical industry. Direct electrification involves the application of electrical energy directly in chemical reactions or physical transformation processes. This includes methods such as electrically heated reactors and electric furnaces used to substitute fossil fuel heating. As an example, you see here the concept of the industrial route for the production of chemicals as performed today on the right side of the scheme. Pictured in grey is an industrial route where fossil resources are used as fuel. On the left side of the scheme, you see the concept of a potential future route. Here, renewables are used for electricity production, which is directly used as an energy source, for example, for heating purposes. Electrical heating may be performed using joule heating, induction heating, or microwave heating. Indirect electrification, on the other side, uses electricity to facilitate the synthesis of chemical feedstock or energy carriers that are subsequently utilized in chemical processes. The most prominent example is hydrogen production by electrolysis. The produced hydrogen serves as an intermediate product that either is used as an energy source or as a process chemical. We will have a closer look at hydrogen utilization on the next slide. Hydrogen with a low carbon footprint is considered a vital alternative feedstock and a future energy carrier. By utilizing hydrogen, not only energy efficiency is enhanced, but also carbon emissions are substantially reduced. However, hydrogen utilization requires that it is affordable and prioritized when replacing unabated fossil-based hydrogen. The European Union aims for 50% share of green hydrogen in the total hydrogen consumption of the chemical industry. The ammonia production requires the largest amount of hydrogen produced today, making it the most relevant industry example. Let us have a closer look at the production scheme when green hydrogen is implemented into this process route. Renewable energy produced via wind, solar or water power is directly used to provide process energy for air separation via the Linde process to generate a pure nitrogen stream. Further, electricity is used for hydrogen production via electrolysis. Hydrogen and nitrogen are used as educts, which are converted in the Haber-Bosch process to ammonia. Ammonia is a base chemical for fertilizer, polymer, colorant, explosive and nitric acid production, to name the most important ones, but can also be used as fuel, for example, in fuel cells. What about other feedstocks in the transition path? When biomass serves as a feedstock in the chemical industry, it is mainly lignocellulosic biomass, agricultural residues or sugars that we speak of. Biomass is considered a carbon-neutral feedstock. However, sustainable sourcing, the linking to processing steps into integrated value chains, potential scarcity, and competing utilization for food supply and as feedstock for industrial production into essential chemicals and fuels are challenges. The complex composition of biomass leads to high costs for chemicals derived therefrom. Therefore, they cannot compete with chemicals from fossil resources. Efficient fractionation, conversion, and downstream processes are hence needed to ensure energy and material efficiency. Carboxylic acids, such as citric or acetic acid, that you know from a kitchen at home, are examples of bio-based chemicals. Levulinic acid is also a carboxylic acid, but has high relevance as a platform chemical. This means that it serves as a building block for educt or further chemical synthesis. Here you see for which purposes levulinic acid is used in industry. But what does the production of levulinic acid look like? You see here the production route of levulinic acid. The biomass and an acid are fed into a continuously stirred tank reactor, where the biomass fractionation takes place. Lignin and humins remain as solids and are filtered off, washed and centrifuged before further utilization, for example, being burned to generate process heat. The liquid stream undergoes a solvent extraction, where the carboxylic acids are selectively transferred to the solvent phase, while the aqueous phase is fed back to the stirred tank reactor. For solvent recovery, first the volatile carboxylic acids, mainly formic acid, are evaporated before levulinic acid and the solvent are recovered in a distillation column. The levulinic acid is recovered in high quality at the bottom of the column and can directly be used in subsequent processes. Not only virgin biomass is used as feedstock, but also waste streams. Waste utilization in the chemical industry refers to the integration of waste byproducts into production processes. Strategies for waste utilization include the conversion of carbon dioxide and organic waste into valuable chemicals, with the main focus being on the circularity of materials. A highly relevant route is the utilization of captured carbon, which is repurposed as feedstock for chemical synthesis. The most prominent reaction is the reaction of hydrogen and carbon dioxide to methanol, which is further used as a bulk or platform chemical in the chemical industry. As can be seen on this slide, the production process includes the use of renewables for energy production in both ways, indirectly to produce hydrogen and directly for process energy. Biomass may also be used for electricity production. Additionally, captured carbon from air, biomass conversion, and from fossil resource utilization enters methanol synthesis. Methanol being a platform chemical in the chemical industry, which is, for example, converted into formaldehyde or methylamine. A second example is plastic waste utilization within the chemical sector instead of plastics being landfilled or incinerated. We will have a look on plastic recycling in another video. Carbon capture and utilization and carbon capture and storage are considered key technological pathways for the decarbonization of the energy-intensive industries like the chemical sector, although challenges related to cost and energy requirements exist. We will have a closer look on CCU and CCS in a future video. Process efficiency refers to the overall effectiveness of chemical processes in terms of resource utilization, energy consumption, and waste generation during the production of chemicals. This can be achieved through process intensification, such applying green chemistry rules, including catalysis, new reactor design, but also resource efficiency measures, such as energy recovery or industrial symbiosis are meant here. Further, the adoption of advanced technologies such as digitalization and automation is crucial. They facilitate real-time monitoring and the optimization of reaction conditions, resulting in reduced energy inputs and enhanced outputs. In summary, in this video we discussed the chemical industry, which is at the center of the European Green Deal. The chemical industry's electricity demand is expected to grow significantly due to the trend towards electrification. Measures to utilize electricity are either direct or indirect utilization. Generally, direct electrification should be prioritized over indirect electrification due to efficiency. With respect to hydrogen production, we saw that hydrogen needs to be produced from renewables to ensure sustainability, so that the carbon footprint of production routes, such as ammonia, can efficiently be reduced. The utilization of biomass for electricity and as feedstock is seen as a need, but remains difficult due to complex raw material composition. Waste utilization, such as captured CO2, for example from methanol synthesis, are proven production pathways. However, infrastructure needs to be built. Carbon capture and utilization and carbon capture and storage together provide essential feedstock for the chemical industry. And lastly, we had a look at process efficiency, where, for example, green chemistry is a measure to ensure decreased impact on the environment. With that, I would like to thank you for watching and hope you got relevant information.